This is John Whitaker for the Mathematical Analysis 2 class, and this is our 17th video lecture. And today, we're going to prove a few theorems about integration. In particular, we're going to do a theorem about Usubstitution, although I'm not calling that. Now, the first thing we look at, we're going to look at two theorems about the fundamental theorem, two parts of the fundamental theorem of calculus. And then I will state integration by parts, but I won't prove it in this video lecture. We'll also do some examples of these integration techniques and facts. So first of all, the Usubstitution Theorem, the book calls it change of variable integration technique. So here it is. Call it the change of variable theorem. Here's what it says. It says, suppose phi is a strictly increasing continuous function that maps the interval capital AD onto little ad. Suppose alpha is monotonically increasing on little a to little b, and f is Riemann-Stieltjes integral with respect to alpha on little a to little b. Then what we're going to do is we're going to define two functions, b, beta, I should say, and g on the interval from big A to big B by, so beta of y is equal to alpha acting on, composed with phi of y, and g of y is equal to f evaluated at phi of y. So that's part of the theorem. We're ready to get to the conclusion of the theorem. Then, g is Riemann-Stieltjes integral with respect to beta, and the integral from big A to B of g d beta is equal to the integral from little a to little b of f d alpha. And as I said, it's called the change of variable formula or theorem, but this is a general form for what we call in calculus Usubstitution. Well, let's look at the proof. So if we let Q equaling y sub 0, y sub 1, up to y sub n be a partition of big A to B, then phi of y sub I, if you look at at that collection, I run from, well, here, 0 to n, forms a partition of little a to little b. Okay. So we can see this is true, as phi of y naught. Y naught's the first guy in the partition Q, and that's going to be equal to A. Well, that has to be equal to little a as phi is onto A to B, and it's increasing. Let me write that down. And phi is strictly increasing. Also, phi of y sub n will be equal to phi of b, which equals to b, as again, phi is onto A to B, and phi is strictly increasing. Now, if we take some partition P equal to x naught, x1, all the way up to xn of little a to b, that interval, I'm sorry, I should have said, I should have written be a partition of little a to little b. Then the inverse function, b of xi, as I run from 0 to n, will form or will be a partition of big A to big B as phi inverse will be onto and strictly increasing. Now, if we let x be an element of A to B, then there exists a unique y that's an element from big A to big B, such that phi of y equals to x. Since as stated in the theorem, we define g of y to be equal to f of phi of y, which equals to f of x. Then the values taken on by f on the subinterval from x of I minus 1 to x of I are the same values are the same values taken on by g on the interval from y sub I minus 1 to y sub I. That subinterval created on the partition of big A to big B. Also, since beta of y is equal to alpha of phi of y, then beta of y sub I is equal to alpha of phi sub y, phi of y sub I, which is nothing more than alpha acting on x sub I. What that gives us is a relationship between upper sums and lower sums with these partitions, corresponding functions, and corresponding alphas and betas. Namely, thus we have that the upper sum with Q, G, and beta, that's going to be equal to the upper sum with the corresponding P, F, and alpha. And the lower sum with Q, G, and beta is equal to the lower sum with P, F, and alpha. All right. Now, we'll let epsilon be greater than 0 be given. Since f is an element of Riemann-Stieltjes integrable function with respect to alpha on A to B, then there exists a P sub 1, which is a partition of little a to little b, such that by that theorem that we've been using over and over again to show integrability, which is if and only if statement. So there's P sub 1 such that the upper sum of P sub 1 F and alpha minus the lower sum with P sub 1, F, and alpha, that's less than epsilon. Okay. Thus, there exists a Q sub 1 of, that's a partition of big A to B. That's the partition that corresponds to, Q sub 1 is the partition that corresponds to P sub 1, and their relationship is given through phi. There exists a Q sub 1 of partition of A to B such that this upper sum with q sub 1, g, and beta minus this lower sum with q sub 1, g, and beta will be less than epsilon. So since I found such a partition of a big integral from a to b, big A to big B, such that the upper sum minus the lower sum was less than epsilon by that main fact, that tells us that G is Riemann's field is integrable with respect to beta on big A to B. And that concludes this proof. I've mentioned that this is a general form of use substitution. What I want to do next is do an example. So if we look at the integral from 1 to 3 of e to the y squared d of y squared. And here's what I'm thinking. So this is our problem. What we can consider is we can say, well, for this problem, big A to B is equal to 1 to 3. We can let phi of y be equal to y squared. Okay? And here then g of y is equal to e to the y squared, which is equal to e to the phi of y. And since we want g of y by what our theorem had to match up with f evaluated at phi of y, then f should be equal to f of x, if you will, should be equal to e to the x. And that way, g of y is equal to e, or to f evaluated phi of y. Because what does phi do to whatever you give it? It takes e and raises to whatever you gave it. And that's exactly what g of y is. Now, similarly, beta is supposed to be equal to y squared, which is really phi of y. So, if we let alpha of x to be equal to x, then beta will be equal to alpha phi of y. Because alpha, whatever you give it, it just yields out the same thing. And so alpha phi of y is phi of y, which is y squared. Okay, so with that type of arrangement, then in our example, as applying this theorem with the change of variable, so we note that phi maps, so phi of y maps, it was here our problem 1 to 3. And what is phi of y? It's equal to y squared. It maps that into or onto, well, it would be 1 to 9. And so this is equal to our little a up to b integral, little b integral. Okay. Then, by the change of variable theorem, what we have is the integral from 1 to 3 of e to the y squared dy squared will be equal to the integral from 1 to 9 of here, this would be e to the x, and then it would be dx, d alpha is dx. Okay. And so that's what we have. And if we can integrate this, which we really can, by the fundamental theorem of calculus, which we haven't done yet, but if we can integrate this, we get the integral of this guy. Now, here's what I'm going to finally leave you with for this example. Note the integral from 1 to 3 of e to the y squared, dy squared, is really, because this is, our beta, the function that we have here, that we're integrating with respect to. And this is a differentiable function. We know that this is equal to, by a previous theorem, from 1 to 3, the interval from 1 to 3 of e to the y squared, and here I take the derivative of this guy, which would be 2y, and then it would be dy. And then normally what we do in calculus to be able to integrate this is we do something called Usubstitution. We let u be equal to y squared. And then the derivative of u with respect to y will be 2y. And so we multiply this by 2y dy. And so the interval from 1 to 3 of e y squared 2y dy, we say from our calculus, will be equal to, well, I'm not going to write the bound yet, but this would be e to the u, and then 2y dy is the du, and then, du. And if we write everything in terms of y, here, in terms of u, here the y values run from 1 to 3. Well, u is equal to y squared. So the u values, which is what I'm writing this integral in terms of, would run from 1 squared, which is 1, to 3 squared, which is 9. And that's exactly the form that we have right here, except the last thing I wrote was in terms of u, where here it's in terms of x. But they're the exact same interval. So that's an example of this change of variable formula being used, and it's just like our u substitution in this case. Okay, the next thing I want to do is do the fundamental theorem of calculus, part 1. So here's what this book lists as part 1 of the fundamental theorem of calculus. It says, let f be Riemann interval on A to B. Now, for any x that's sandwiched in between A and B, put big F of x equal to the interval from A to x. A little f, we'll give a dummy variable here, t dt. Then, f is continuous on A to B. That's something we need to prove. Furthermore, if f is continuous, little f is continuous at a point x naught, element of A to B, then f is differentiable, big F is differentiable at x naught, and I can tell you what the derivative of big F is. So the derivative of big F of x naught is equal to f, little f evaluated at x naught. So that's what we want to prove. So two things really in this thing. Continuity of big F and its derivative. Okay. Now, we'll start off with, we're assuming f is Riemann interval function on A to B. So since that's true, that's one of the hypotheses of the statement. Then, to be talking about this, we know f is bounded on A to B. Okay? So, we suppose the absolute value of f of t is less than or equal to m for all, or for a less than or equal to t less than or equal to b. So, if we have a is less than or equal to x is less than or equal to y is less than or equal to b. So here, I'm just taking two guys in the closed interval from a to b, x and y, one is bigger than the other, same as the biggest. Then, if you look at f, that's the value. So we're trying to show continuity here, big F. If you look at f of x, that's right, f of y minus big F of x inside absolute values. Okay. Well, what that's going to be equal to by the definition of big F, that's the integral, absolute value of the integral of a to y, little f of t dt, minus the integral from a to x, a little f of t dt, which we can rewrite as the integral from a to x of f of t, that's the value of it, dt, minus the integral from x to y of f of t dt, and then minus the integral from a to x of f of t dt. Look, this is coming from, these two parts here are coming from this one integral here. And what I'm doing is I'm using a fact that we proved earlier about Riemann-Stieltjes integral, which the Riemann integral is a special case of. It said if you go from A to C, from A to B, that can be broken up from A to C. Broken up from A to C and then C to B. And that's what I'm doing here, because X is in between A and Y. So that's where I can break that up. And of course, these two guys would cancel with each other, and so this is equal to, if you will, just the integral is minus the integral from x to y, but I'll just rewrite that as plus the integral from x to y, because the absolute value of it is the same thing as the absolute value of the positive version, of f of t dt. Now, this is less than or equal to m times y minus x. Yeah. That's a true fact. Now, if we let epsilon be greater than 0 be given, remember we're trying to show that big F is continuous, okay? So we're looking for this delta. Then what I'll say is, whenever the absolute value of y minus x is less than epsilon over m, so epsilon's positive, m is going to be positive. This is acting like the delta involved in the definition of continuity. Then the absolute value of f of y minus f of x, which we know to be, by our previous work, to be less than m, less than or equal to m times y minus x. But y is bigger than x, so y minus x is the absolute value of y minus x. Well, that's less than m times epsilon over m, so I'm substituting in for this, that guy, so it makes it bigger, which is equal to epsilon. So this guy is less than epsilon whenever this occurs. That tells us, so F is continuous. on the closed interval from A to B. And really, what that says then is, thus F, big F, is uniformly continuous. So I'm writing here a stronger conclusion on A to B. Because we know that continuity on a closed set here, on a compact set, implies uniform continuity. Okay, the next thing we need to show is about the derivative of big F. Sorry. Now suppose F is continuous at x sub naught. We want to show that big F prime evaluated at x sub naught is equal to f of x sub naught, little f evaluated at x sub naught. That is, we want to show that the limit as t goes to x sub naught, so I'm talking about this guy's derivative, of f of t minus f of x naught, yeah, we're going to the derivative, chapter 5, which we covered, over t minus x naught, we want to show that that's equal to little f evaluated at x naught. Okay, so this is the limit, so how are we going to do that? We're going to let epsilon be greater than 0 be given. Okay. And what we need a delta bigger than 0, such that here, for all t, element of, this is a t, element of a to b with 0 being less than, that's the value, t minus x naught being less than delta. Definition here that we use for a limit of a function, for a real value function in R. So R is our metric space. Then that's the value of f of t minus f of x naught all over t minus x naught minus little f of x naught. Okay, that's the value of that difference. It's got to be less than epsilon. Well, what we turn to is that little f is continuous. At x naught. There does exist a delta bigger than 0, such that for all t element of a to b with t minus x naught being less than delta, then, well, f of t, little f of t, minus little f of x naught, inside absolute values, will be less than epsilon. Now we're going to look at two cases. So case 1 is when t is bigger than x naught. Look at this case. Then, when we look at that absolute value of big F
of t minus big F of x naught over t minus x naught minus little f evaluated at x naught. Okay, we can get a common denominator here. That's equal to absolute value. Well, I'm sorry, I should rewrite this in terms of the definition of big F. It's the integral from a to t of little f of, I'm going to call it u, du, but I'm not going to write it down to du, minus the integral from a to x naught of f of u, all over t minus x naught, minus little f of x naught. We'll work with that a little bit more over here. All right, that's going to be equal to the integral, absolute value of the integral, let's say t is bigger than x naught, so really this is going to be x naught to t of little f of u du over t minus x naught minus f of x naught, getting a common denominator now. This is the absolute value for the integral from x naught to t of f of u du minus, here's f of x naught times t minus x naught, and that's all over t minus x naught. And so this is in absolute values, and that's going to be equal to, well, I can pull out the 1 over t minus x naught. T minus x naught is positive because t is greater than x naught in this case. And so we have the absolute value here. And I'll rewrite this as the integral from x naught to t of f of u du. And then, you know, x naught, little f of x naught is a constant. And so, really, this is minus the integral from x naught to t of f of x naught du, which we could rewrite as 1 over t minus x naught, because this integral is equal to this quantity here. Absolute value, now combining these two by properties of integration, this would be the integral from x naught to t of f of u minus f of x naught du. And I need to end the absolute values here. Okay, that's what we have. So this is the ending of the absolute values. Okay? Now, if absolute value t minus x naught is less than delta, because of the continuity of little f, then the absolute value of big F of t minus big F of x naught over t minus x naught minus little f evaluated at x naught, that guy, which is equal to this, okay, will be, I'll write that down, 1 over t minus x naught times absolute value of the integral from x naught to t of f of u minus f of x naught du. But look, because of continuity at x naught, and if t is really close to x naught within delta, then the output values here for f of u, they're going to be really close to f of x naught. So this is equal to, that's what value at the end, 1 over t minus x naught. And here I can substitute in epsilon for this part. So it's the absolute value of, well, the integral from x naught to t of this part right here. Well, here, let me say it's less than or equal to. Let me do an intermediate step. It's less than or equal to, I can bring the absolute values inside the integral. So it's f of u minus f of x naught du. And then because the t minus x naught is less than delta, that's going to force these u values to be within delta units of x naught. When that happens, this absolute value between little f of u and f of x naught, that's going to be less than epsilon. So I'll make that substitution over here. Okay. So this is less than 1 over t minus x naught times the integral from x naught to t of epsilon du, which is going to be equal to, and this is a constant, so when we integrate with it, well, this constant listed, but when we integrate here, we're going to get epsilon times this distance, which is t minus x naught. These two guys cancel, which equals to epsilon. Ha-ha. So that shows, in this case, that big F of t minus big F of x naught over t minus x naught minus f of x naught is less than epsilon when the absolute value of t minus x naught is less than delta for this particular delta. There exists stuff to make this happen. So in case 2, remember this first case was when t was bigger than x naught. So case 2 is that t is less than x naught. Then this f of t minus big F of x0 over t minus x0, which is involved in the limit as t goes to x to compute the derivative of big F of x naught, minus little f of x naught, okay, again, is equal to the integral from a to t of it's little f of u minus the integral from a to x naught of little f of u over t minus x naught minus f of x naught, which, because t is less than x naught, this will be the absolute value. Here I'll write this down as one integral, and really it's the integral from, it'd be minus t to x naught of f of u du. That's minus this. All over t minus x naught minus f of x naught. That's what we have. Okay. Okay, and that's going to be equal to, if you will, the absolute value. If we apply that minus sign to the bottom, we're going to have x naught minus t. Here's the integral from t to x naught, f of u du, and then getting the common denominator of x minus t naught, this will be minus f of little f of x naught times the quantity x minus t naught. Again, using the same logic we did before about this guy really equaling to an integral. I can, this should be over x naught minus t naught. Okay? So I pull out the 1 over x naught minus t, it's not t naught, it's just t. Okay, and that the absolute value of this part is itself because x naught is bigger than t. This is the absolute value. Here's an integral from t to x naught of f of u. And here, this is minus the integral. We've already pulled this part out, but it's from t to x naught of f of x naught du, which we can rewrite as 1 over x naught minus t. Here, this is the integral from t to x naught of f of u minus f of x naught du. All right, and here, if we have, if t minus x naught is less than the delta because of the continuity of little f, then we have the absolute value of f of t, big F of t, minus big F of x naught all over t minus x naught minus little f of x naught will be equal to, I'm just going to write down this line here. That's going to be equal to 1 over x naught minus t times the absolute value of the integral from t to x naught of f of u minus f of x naught du, which is less than or equal to 1 over x naught minus t integral from t to x naught of f of u, that's the value of f of u, minus f of x naught du, which is going to be equal to 1 over x of naught minus t. Here, this is integral from t to x naught, and because of the continuity, and u being within delta units of x naught, the continuity of f, little f at x naught, this is going to be less than epsilon du, which equals to 1 over x minus t, or x naught minus t. This is going to be epsilon times x naught minus t, which equals to epsilon. So, in all cases, big F of t minus big F of x naught over t minus x naught inside absolute value, but minus little f of x naught, little f of it, will be less than epsilon whenever the absolute value of t minus x naught is less than delta. It's got to be bigger than 0. And that says that big F prime evaluated at x naught is equal to little f evaluated at x naught, and that's the end of this proof. Well, that'd normally be a decent place to stop, but I want to really cover 2 more things today so that we have all the information that's going to be covered on test 2 essentially here. Ending with video 17. Okay, so the next thing I want to do is the fundamental theorem of calculus, part 2. Well, I guess I want to do something else first. So first of all, I want to do an example of the fundamental theorem of calculus, part 1. So here, if we let big F of x be equal to the integral from 2 to x of sine of t dt, I'm sorry, over t dt, then what we get is f prime of x will be equal to sine of x over 2 over t over x. That's what this fundamental theorem of calculus part 1 gives us. Okay. Now here's the second fundamental theorem of calculus. Fundamental theorem of calculus. Part 2. And what it says is if f is Riemann integrable on a to b, and if there is a differentiable function let's say big F, okay, on A to B, such that big F prime equals to little f, then the integral from A to B of f of x, little f of x dx is really equal to f of b minus f of a, which we often write as f of x evaluated from A to B, like this. It's the fundamental theorem of calculus part 2. And it's not very long. Let's look at it in terms of its proof. So here, if we let epsilon be greater than 0 be given, choose a partition let's call it script P of, well, let it be equal to x of 0, x of 1, all the way up to x of n of A to B. Such that the upper sum with this partition and f minus the lower sum with this partition and f is less than epsilon. Of course, I can choose such a partition because of that main fact that we've proven to be Riemann integral, to be Riemann Tildes integral, if you will. That there's some partition such that the upper sum and the lower sum minus the lower sum is going to be less than what if given epsilon was given. Well, the next thing I want to tell you is that the mean value theorem applied to big L furnishes points points t sub I in the subintervals from x sub I minus 1 up to x sub I such that f of x of I minus big F, evaluate x of I minus 1. So we're using the mean value theorem on big F is equal to big F prime evaluated p sub I times x of I minus x of I minus 1. All right, but that's equal to little f evaluated pi, because big F prime is equal to little f, and then this is times delta x sub I. Okay, so what that gives us is that the sum, as I runs from 1 to n, of little f of p sub I times delta x sub I is equal to the sum as I runs from 1 to n of, here this would be, well, this part is this part, which is equal to this part, so it's the sum of big F of x sub I minus big F of x sub I minus 1. Okay? But that's, you would have a lot of cancellation that would happen between these terms if you let I start running from 1 to n. And what you end up getting is just f of b minus f of a. Okay? So, by previous theorem, here's what we have. The absolute value of the sum as I runs from 1 to n of f of ti and delta x sub I minus the interval from a to b of f of x dx, this part, will be less than epsilon. That's what we have. That is the absolute value of f of b minus f of a minus this interval from a to b of little f of x dx. That is less than epsilon, where epsilon is some positive number. Well, what that tells us, because epsilon is arbitrary, then f of b minus f of a must be equal to the interval from a to b of f of x dx. And that concludes this fundamental theorem of calculus. Well, I'd like to do some more. And that includes listing of some functions whose derivatives are things we might be integrating. So let me just remind you of some things. Might be helpful in the homework. So, if f of x is equal to x to the n, let's say big F of x is equal to x to the n plus 1 over n plus 1, then f prime of x is equal to x to the n, which might be some little f of x. So if you integrate little f of x, if I integrate from 1 to 3 of, let's say, x to the n dx, that's going to be equal to x to the n plus 1 over n plus 1 evaluated from 1 to 3, which would be equal to 3 to the n plus 1 over n plus 1 minus 1 to the n plus 1 over n plus 1, okay, for any fixed n. That's what we have. Another thing is if f of x is equal to, let's say, sine of x, then its derivative will be the cosine of x. This could be helpful. If f of x is equal to e to the x, its derivative will be equal to e to the x, and these could be little f of x, is that we might be integrating. And we could use the fundamental theorem of calculus. Last thing I want to do is just state the integration by parts formula during this video lecture. So here's the theorem. We'll prove it next time, and you won't be responsible for the proof. Okay? I'm not going to ask you to do the proof for this test. But this is the integration by parts formula. Oh, wait, I'm sorry. Before I did the integration by parts formula, before I say, let me do one more example. No, I'm ready to state the integration by parts formula. So here it is. Sorry. Here it says. It says, suppose F, big F, and big G are differentiable functions on A to B. Big F prime is equal to a little function called little f, and big G prime is equal to a function called little g, where little f and little g are Riemann integrable. Then, the integral from A to B of big F times little g will be equal to big F, evaluate B, times big G, evaluate B, minus big F, evaluated A, times big G, evaluated A, minus the integral from A to B of G prime, big G prime of X, I'm sorry, big G of X, I said the wrong thing, times little f of X dx. That's what it says. And I'm going to prove this later, but next video, and I want to do one example. I want to do an example because it turns out this integration by parts formula is something that can help you in the last problem, in the homework. Let me do an example of it. We'll call it this example. Integrate from 0 to 1, x times cosine of x dx. You say, well, what's this integral? Well, here's what you do. You can let big F of x be equal to x, then big F prime of x will be equal to 1, which is the little f of x. And then here we say g, little g of x be equal to cosine of x. It turns out that big G of x would have to be the sine of x. Okay. Then, by the integration by parts formula, what we have is the integral from 0 to 1 of x cosine of x dx will be equal to, so it is f times g, so it would be f will be x, the f of here 1 times g of 1 minus f of 0 times g of 0 minus the integral from 0 to 1 of here is a big G, which is sine of x, and then times little f, which is just 1, dx. And if you don't mind, this is going to be equal to, so f of 1, that's going to be 1, g of 1 is going to be sine of 1, then f of 0 is 0, this part's 0. 0 times g of 0 is going to be 0 as well. Minus, well, integral of this guy, an antiderivative of this using fundamental theorem of calculus, really it's going to be a plus cosine of x evaluated from 0 to 1, so I get a final answer of sine of 1 minus 0 is just nothing. And then here it will be plus cosine of 1 minus then cosine of 0. And so I write this down as sine of 1 plus cosine of 1 plus 1 itself. And that's my answer. I know this has been a long video. I want to thank you very much for your time and patience.